Hello everyone, so today we will be learning about acid-base equilibria. Before anything else, let us have a little review about the properties of acids and bases. So how would we know if a solution is acidic or basic? So usually these are the properties of acids and bases. So acids, usually they have a sour taste, their pH is less than 7, and then a blue litmus paper turns red if the solution is acidic. And then if we will be using phenolphthalein as our color indicator, acidic solution remains clear. Now for bases, they are bitter to taste, slippery, its pH is greater than 7, and then a red litmus paper turns blue if the solution is basic. And then if we will be using phenolphthalein as our color indicator, basic solution turns pink. Now we will move forward to Arrhenius' definition of acids and bases, which was developed by Svante Arrhenius. So according to this definition, an acid is a substance that, when dissolved in water, increases the concentration of hydrogen or hydronium ions, while a base is a substance that, when dissolved in water, increases the concentration of hydroxide ions. So according to Arrhenius' definition of acids and bases, there are two things that we must take note of. For an acid, we must take note of if it increases the concentration of hydrogen or hydronium ions. Now, for it to be considered a base, it must increase the concentration of hydroxide ions. Now, our next definition is the Bronsted-Lowry acid-base definition, which were independently developed both at the same time by Johannes Bronsted and Thomas Lowry. So, according to this definition, a Bronsted-Lowry acid is a proton donor and a base is a proton acceptor. Now in here, we can see that a Bronsted-Lowry acid in the form of hydrochloric acid, okay, must have at least one removable acidic proton in the form of hydrogen ion that will be donated to our base, wherein a Bronsted-Lowry base must have at least one non-bonding pair of electrons to accept a proton. So what will happen when an acid dissolves in water? Water can act as a Bronsted-Lowry base and it will abstract a proton from the acid. As a result, the conjugate base of the acid and a hydronium ion are formed. Now we have here the relative strengths of acids and bases. On the left side of the screen, we can see here the strong acids and the weak acids, while on the right side, we have here the weak bases and the strong bases. So acids above the line with water as a base are strong acids. So these are our strong acids. We have hydrochloric, sulfuric, and nitric acid. And their conjugate bases do not act as acids in water. Now bases below the line with water, so these are our strong bases, their conjugate acids do not act as acids in water. So for example, we have here our oxide, and then this is its conjugate acid pair, which has a negligible acidity. The substances between the lines with water are conjugate acid-base pairs in water. Aqueous solutions can either be acidic, basic, or neutral. So how would we know? If a solution is neutral, then hydrogen ion concentration is equals to hydroxide ion concentration. If a solution is acidic, then hydrogen ion concentration is greater than the hydroxide ion concentration. And if a solution is basic, then the hydrogen ion concentration is less than the hydroxide ion concentration. So do not forget these three important points. This will give you a hint or an idea whether a solution is acidic, basic, or neutral. Next, we will be discussing the pH scale. So when we say pH, it is simply a method of reporting hydrogen ion concentration. So pH has the following formula. pH is equals to the negative logarithm of hydrogen ion concentration. So whenever you see this bracket, it simply means concentration. So now let us put into use our new discovered formula about pH. For our practice exercise, I want you to calculate the pH values for the two solutions below. First, a solution in which the hydrogen ion concentration is found to be 0.010 molars, And the other one is a solution in which the hydrogen ion concentration is found to be 1.8 times 10 raised to negative 9 molars. So I will be giving you time to calculate for the pH of these two solutions. So remember, in calculating, our formula is pH is equals to the negative logarithm of hydrogen ion concentration. So what you will simply do is to substitute the concentration of hydrogen ions into the equation and then plug it in your calculators and you will get the value. So for our first solution, the pH is equals to 2.00. Now for reporting your answers with correct significant figures, the significant figures for pH are the digits after the decimal point. So knowing that our given has two significant figures, so our final answer should have two significant figures after the decimal point. So for our first solution, the pH is 2. And then for our second solution, the pH is 8.74. Now another one for pH calculation. So suppose, for example, that the pH of Coke is 3.12. What is its hydrogen ion concentration? So this time, we are being asked about the concentration of hydrogen ion. Because pH is equals to negative logarithm of hydrogen ion concentration, then we will be modifying this equation to be able to get the concentration of hydrogen ion. So transferring the negative to the other side, we will have negative pH is equals to the logarithm of hydrogen ion concentration. So we will take the anti-log of both sides, and now we will be having this new equation. So the hydrogen ion concentration is equals to the anti-logarithm of negative pH. Substituting pH, we will be able to calculate for the hydrogen ion concentration, which is 7.6 times 10 raised to negative 4 molars. Now, to find the antilog or anti-log on your calculator, look for the shift function or the second function and then the log button. And then this 10 or the anti-log will appear in your calculators. Okay, so let us have another example. So we have here a solution that has a pH of 8.50. What is the molarity of hydrogen ions in the solution? So from our previous calculation, we know that in order to calculate for that, we have this new formula wherein the concentration of hydrogen ion is equivalent to the anti-logarithm of negative pH. So knowing that, we will just simply substitute our value, which is 8.50, and then plug it in our calculators, and we will be getting this concentration of hydrogen ions, which is 3.16 times 10 raised to negative 9 molars. Now let us discuss the other P scales. So the P in pH tells us to take the negative logarithm of a quantity. So for this case, we have hydrogen ions. So some other P systems that we have are the POH and the pKw. So when we say POH, it is simply equivalent to the negative logarithm of the hydroxide ion concentration. So this time, it takes note of the hydrogen ion or the hydroxide ion concentration. Now the pKw, Kw is for water dissociation constant, is equivalent to the negative logarithm of Kw. Autoionization of water. So Kw is actually equals to the product of the concentrations of the hydronium ion and the hydroxide ions. So we know that water has a very specific property in which it autoionizes. So it separates into hydronium ion and hydroxide ions, and it forms an equilibrium reaction, which is equivalent to 1.00 times 10 raised to negative 14 molars at room temperature or at 25 degrees Celsius. So in neutral solution, hydronium ion and hydroxide ion concentrations are equal. And so, If they are equal, then their concentration at 25 degrees Celsius is 1.00 times 10 raised to negative 7 molars. Since acids and bases are opposites, pH and pOH are also opposites. pOH does not really exist, but it is useful for changing bases to pH. So pOH looks at the perspective of a base. So we know that pOH is equals to negative logarithm of hydroxide ion concentration, and pH is equals to negative log of hydrogen ion concentration. And then from the previous slide, we know that at neutral solutions, the concentration of hydrogen and hydroxide ions are equal. So then, pH plus pOH is equals to 14. So this is now another equation that we will be adding to the previous equations that we have learned. Okay, so let's try using our new discovered formulas. What is the pH of 8.001 molar NaOH solution? So analyzing this problem, we are given the concentration of a base. So knowing that what we have is a base, we now know that the hydroxide ion concentration is 0.0010 molars. So from here, we can be able to calculate for pOH. So the pOH is 3. So now that we have pOH, we have another formula which says or which states that pH plus pOH is equals to 14. Now if we will be modifying this formula, we will be able to get pH. pH is actually equal to 14 minus pOH. We have calculated the value of pOH as 3, so substituting that into the equation, 14 minus 3, we now get our pH value, which is equals to 11. So a solution whose concentration is 0.0010 molars of NaOH has a pH value of 11, which is true because NaOH is a strong base. Okay, so let us try another one. A sample of freshly pressed apple juice has a pOH of 10.24. Calculate hydrogen ion concentration. So this time we are given the pOH and we are asked to calculate for the hydrogen ion concentration. So knowing that, we modify the equation to get the value of pH, which is equals to 14 minus pOH. So we substitute pOH into the solution. So we subtract 10.24 from 14, and we now get our pH, which is equals to 3.76. Now that we have pH, we now use this other formula equation, wherein hydrogen ion concentration is equivalent to the anti-logarithm of negative pH. So we simply substitute pH. So anti-logarithm raised to negative 3.76, we now get the hydrogen ion concentration, which is equals to 1.74 times 10 raised to negative 4 molars. Okay, so how do we measure pH? So this is usually done in the laboratory. So indicators, which includes litmus papers, are used for less accurate measurements. So an indicator is one color in its acid form and another color in its basic form. So the most common color indicators that you have already experienced using is the phenolphthalein. So we also have methyl red and the promphenyl blue. Now, pH meters, on the other hand, are used for more accurate measurement of pH. So the electrodes, they indicate small changes in voltage to detect pH. So this is how we measure pH.